Good morning, chemistry team. Here we go with video number 7 in our buffers titrations. Really, this whole chapter is about titrations. We just need to know what buffers are in order to calculate the pH anywhere along the point of a titration curve. Now, in lab, you've all probably used phenolphthalein for an indicator, which we know is acidic. It's colorless in acidic solution and this pink in basic solution, so you're trying to get this faintest pink color. Some of you may have used different indicators, but highly unlikely at the undergraduate level, I would imagine. But there's a whole ton of pretty cool colors out there. So I want to focus just a video on indicators themselves and how they work and why they're different colors in different solutions. And now we're going to get some choices. Back in first semester of general chemistry and prep chem, we chose your indicator for you ahead of time. And remember, the point is because we want the end point, the color change of the indicator, to match the equivalence point of the titration we're doing when the acid and the base neutralize each other. Well, at the kind of the earlier levels of chemistry, we haven't learned how to calculate the pH at the equivalence point. So we didn't even think about, where is it at pH 7, pH 9, pH 4? Oh, I don't know. So phenolphthalein we choose because it's a very common one and it's easy to see colorless to pink or the faintest pink color, but may not be the best indicator for every possible titration. So in second semester of general chemistry, we're going to learn how to choose the most appropriate indicators. And sometimes the best one that appears to be viable may not be the one we use because of costs, maybe because colors. Like I said, it's always easier for a human to look for a colorless to a color rather than a color to another color. So that's why phenolphthalein is really popular. But in general, they are pretty complicated organic acids or bases. The structures are insane. I'll draw some up in a second, but we haven't had organic yet, so it's like, this is crazy. But if you can do loose structures, you get a feel for them. But I'll show you what they look like in acidic and basic solution. But what happens, the reason the colors change is you have this complicated organic structure. Maybe it looks like this in acidic solution, and when it becomes basic, it goes, and it changes its structure and interacts with the light a little bit different, so you get a different color. And again, we use these most commonly for titrations at this level so that we can use this endpoint. Its color change doesn't really tell us a pH. It just tells us, hey, we're done. Stop adding your titrant. Right? We've hit the equivalence point. Stop adding. But sometimes you'll see indicators, soaked into paper. If you've ever seen pH paper before, it's like these white strips of paper. And they soak an indicator into it and dry it up. And so you use that pH paper, and when you dip a solution, the water from the solution gets in there, and then the colors come out based on the pH. It's kind of cool, and you can kind of estimate a pH, not accurate like a pH meter, but you can tell, it's around a pH 4, around a pH 8 based on the colors. Sometimes you'll see little strips for testing swimming pools or soil acidity. So lots of good use for indicators. But for us right now, we're just going to use those to find an endpoint that hopefully matches the equivalence point of our titration. So let me show you just some quick structures of phenolphthalein, kind of why its structure changes in acidic versus basic solution, and then how to utilize these color changes to our advantage. Ready for some organic headaches here, guys? Yeah, this is what you're going to get in organic chemistry next semester. Yay, fun! There's just a Lewis structure, but it's a big messy one. So let's take phenolphthalein, which is the one you're probably used to, and it depends on the acidity. So let's look in acidic solution, and we know it's colorless in acidic solution. So you can see, do you remember the benzene rings? Right? So we got the 3 double bonds in the ring there. With a carbon in the middle, we got this carbon double bond O, and we got this oxygen bridge here, an OH group there, OH group there. So that's what it would look like in acidic solution. But let's say we start adding some sodium hydroxide, becomes more basic, less acidic, more basic, right? You start to see some subtle changes here. Notice this bond breaks, right? Boop! And if you want to learn why, take organic chemistry. So we end up with a double bond there and an O with a negative charge, right? So that oxygen ends up having a negative charge, and that OH group turns into a double bond oxygen there. And if you want to look up the functional groups and all that fun stuff, take organic chemistry. All I need you to know for this class is the structure changes. And because that structure changes, now it interacts with light differently, and in basic solution, it has a pink color. So all the indicators, you know, are fairly complicated structures with these subtle changes between acidic and basic solution, and those create really cool colors. You get a neat variety of indicators and colors. But would you agree with me at this level? These structures are a pain in the butt. All right, so can we just summarize these and just say, hey, let's say we have just any indicator. We don't care what indicator it is, just some generic indicator. So let's say this is in acidic solutions. So can we just call this HIN, right? So think of it as a weak acid. So it's instead of HA, like we do a generic acid, we'll just go HIN. So it's the acidified form of any indicator. And then in basic solution, we lose that, form its conjugate base, right? So let's call this IN minus. So it's kind of like a weak acid conjugate base pair. That's all it is. A little more complicated though. Let's use these forms rather than these forms. Are you good? Are you good? Are you good? Okay, let's do that. Let's go and show you a little bit more. Wow! All right, I think you guys are going to like this a little bit better than those crazy Lewis structures, all right? So let's just say we have the acidified form HIN of the weak acid, and then the conjugate base form in basic solution. We actually, since it's a weak acid conjugate base, could we just set up an equilibrium here, right? So that would ionize in solution. So this is pH dependent, would you agree? So if we increase the amount of acid, H3O plus, Le Chatelier's principle, it shifts over to the left and dominates in the acidified form. If it becomes more basic, say we're adding OH minus, and it reacts with the H3O plus and drops this, if this goes down, it shifts this way. So in basic solution, you're shifting to the right, and you get more of the conjugate base form. Oh! Roughly with our pathetic human eyeballs, if it's about 90, if we shift it to the left, because it's low pH, lots of hydronium ions, very acidic, and we're about 90% or more this form and maybe 10% or less of this form, we're going to perceive that as its color in acidic solution, like phenolphthalein would be colorless or something. We'll call that the acidic color. And if we add lots of sodium hydroxide or another base, we're pushing it this way. And let's say we end up with a dominant form of the conjugate base IN minus, about 90% this, less than 10% that, right? Then we're going to dominate the color in basic solution. We'll call that the basic color. So phenolphthalein, that would be pink. Right? If we're about half and half, right? So about 50% roughly the acidified form, 50% the conjugate base form, we're going to get this intermediate color between the two. And a lot of times when you're in lab, it's just this flashing color change. A lot of times you don't even see it, you miss it. Well, that range, our eyeballs can perceive that over about a 2 pH range. So that color change isn't just boom, it happens over a range. But what we'll find out with our titration curves, the pH changes so dramatically with a drop or two, more than a 2 pH unit change. Well, as long as this 2 pH change, color change of the indicator falls within that big steep middle part of the titration curves we showed you in the last video, we're good to go, right? You might have a 4 or 5 pH change in the titration curve right here, right around the equivalence point here. And so the indicator change could fall here, here, here. So there might be 2 or 3 different indicators that fall within that steep rise. And we'll find out that the steepness of that depends if it's weak acid or weak base, or a strong acid or strong base that we're titrating. We'll find out the stronger ones have a steeper rise, so you have more choice of indicator. But couldn't we, because this is like a weak acid, couldn't we write an equilibrium expression for this? So couldn't we say that instead of Ka, let's just go K indicator? Well, you take we don't include the liquid, right? So this would be the concentration of the hydronium ion raised to the power of 1 times the conjugate base form of the indicator raised to the power of 1 over the weak acid form of that indicator raised to the power of 1. So we can set up an equilibrium expression for this. This is why you don't want to add a ton of indicator, because it is a weak acid in and of itself. And just like we did for weak acids, if we've got roughly equivalent amounts somewhere in there in that range, we can estimate, we can bypass ice tables and go straight to the Henderson-Hasselbalch equation like we did for buffers. And so if we write that, we could say, if you go through and derive that, what was that equation? pH is pKa, and we'll go pK indicator this time, plus log of the conjugate base form over the weak acid form. So that's similar to the Henderson-Hasselbalch equation. So just replace Ka with K indicator, and the conjugate base form, instead of A minus, you put IN minus. Instead of HA, you put HIN. We can see if the concentrations are the same, this log of 1 becomes 0, and so the pH is equal to the pKa of the indicator right in there. All right? And then as we start pushing this to about 90% this, 10% that, we push it about a tenfold change here. And if we switch that, we get about a tenfold change going this way in acidity. And that gives roughly about a plus or minus 1 pH range that our eyes can see. So that's why we have about a 2 pH range, plus or minus 1 pH on either side of the pKa at the intermediate color. That doesn't make sense, not that big a deal. I'll show you how to do that on the pH titration curve when we plot the pH versus the volume of the titrant. All right, so what we're going to do is take a look at a picture of all this fun stuff, and you can look up, you can probably find tables of the Kas of different indicators. I'm not going to really test you on this on exams. I just want you to know how to choose an appropriate indicator, so you don't need to know all this fluffy stuff. But again, it's about a 2 pH range there. Let's look at a specific example, right? Bromocresol green. You can pick any of them, doesn't really matter. And again, we're not going to use those complicated organic Lewis structures. Let's just say here's the acidified form of bromocresol green. Here's the conjugate base form of bromocresol green. And just rewriting what I did before, this would be the intermediate color, about half and half, right? So if it's half and half, those are roughly equal to each other. That drops out. pH is roughly equal to pKa. So for bromocresol green, let's say we look up the Ka value for that weak acid indicator. It's 2.1 times 10 to the minus 5. Okay, well, what's pKa? So take the negative log of 2.1 times 10 to the minus 5, and I rounded it up to, it's like 4.67 something, 77 something. So it's about 4.68, right? Good to 2 decimal places there. 2 sig figs gives us 2 decimal places. But if we put it in an acidified solution with a very low pH, this dries up, it shifts it this way, and let's say we push it to about 90% of the weak acid form, less than 10% of that form. All right? Well, that 10 to 1 ratio would subtract about 1 from this, so we'd get the pKa minus 1, so 4.68 minus 1 would be about 3.68, give or take. This would be the acidified form, and I don't have a yellow pen, but that is roughly yellow color for bromocresol green. If you're at the intermediate color, right, around a pH 4.68, it's about green, right? That's why it's called bromocresol green. That's its intermediate color. But let's say we add base to it. We're titrating an acid. We put a couple drops of bromocresol green. It starts as yellow. It will flash green. You probably would miss it and start turning its basic color blue once you're past the end point. You get past the equivalence point and you push past the end point too far. It becomes more and more blue. So it starts as yellow, turns greenish, then bluish. So if we push it where it's about 10 times, we got about a tenfold factor more of this form, so about 90% IN minus. Then this becomes pKa plus 1, so 4.68 plus 1 is about 5.68. That would be the basic form of blue. And there are really, so if you look in your textbook, there are really cool tables, and you can find them all over the place, of indicator colors, right? You see all those indicators, right? So if you look for bromocresol green, I can't read right there, bromocresol green, right? You can see it starts as yellow, right around the pH we talked about, right? 3.68, it's close to 4, so bromocresol green, right in the high 3 range there. And then it turns kind of a greenish right around the 4.68, turns blue right about the 5.68, and then it's blue from that point on. Anything below that's yellow. And so you can see your phenolphthalein up here, right? So it's colorless at pHs below about 8, and then shifts into kind of a darker pink to a red color when you're pH above 10. So if you add too many drops, it's way too pink to reddish, right? You want the faintest pink color to get that change. So what you do is we're going to calculate the pH at the equivalence point for different acid and base titrations and find where that pH lies. Okay, and there's going to be a huge range where it shifts in pH about that equivalence point, and we just want to pick a 2 pH range for the indicator that falls within the range of that steep rise in that equivalence point. So you got a lot, and this is just a small table. There's a whole bunch of choices. I'll give you a table on exams. Not going to be a nice color-coded table, all right? But I'll give you a table, and when you calculate the pH at the equivalence point of a titration, you can just go on that table and find an indicator whose 2 pH unit range falls within the range of the steep rise around that equivalence point. And you're good to go. And there might be 2 or 3 valid answers. I'll take them all. It's good for me. All right, so that's enough for indicators. Let's get to some titration curves. We'll start with the easiest one first, strong acid with strong base.